Hello and welcome back. We'll finish off this section by starting to look at rational functions. And again, a rational function is going to be a polynomial divided by a polynomial. And rational functions are quite nice. They are going to be smooth. They're not going to have any sharp corners in them. But they can have asymptotes. They're not going to be continuous. So here, this is the graph of 1 over x. And we can see that, yes, we have this asymptote at 0. We're going to be dividing by 0, which is not good. So the function is either going to shoot off toward negative infinity if we approach 0 from the left, or shooting off to positive infinity if we approach 0 from the right. And what you'll notice is that on both sides of the asymptote, we switch from being negative to positive. So the function is negative when x is negative, and the function is positive when x is positive. So we can switch from being negative to being positive. Here. So when we want to look at rational inequalities rather than just polynomial inequalities, the sign can switch not only at a 0 of the function, but also at the asymptotes, at the vertical asymptotes. So there's just an extra step here. Not only do we need to find all the zeros of the function, but we also need to find the asymptotes. So let's do that for this rational function. We've got 2x over x plus 1 is greater than or equal to 1. We want to know when is this true. So just like with polynomials, we want to get everything on one side. So we'll subtract 1 from both sides. Get that this is greater than or equal to 0. And when we look at this, this is now no longer, it doesn't look like a rational function. It doesn't look like a polynomial divided by a polynomial. So what I want to do is to turn this into a polynomial divided by a polynomial by combining these terms. Now, I can't just subtract 1 from this. I need to rewrite 1 as a fraction with a common denominator. Well, 1 is a nice number to do this with, because 1 is the same thing as something divided by itself. So I can rewrite 1 as x plus 1 divided by x plus 1. And that means that I can combine these these fractions with a common denominator. Write this as a bigger fraction. So now this whole thing will be over x plus 1, and I'll have 2x, and I want to subtract the top of this fraction. So I'll have 2x minus x minus 1. This will be 2x. I need to distribute the negative sign. And I can finally write, this will be x minus 1 over x plus 1. And I need to find where this is going to be greater than 0. Okay, so what I want to do is I want to find the asymptotes and the zeros of this function. So for the zeros, when is a fraction equal to 0? Well, when the top of the fraction is equal to 0. So all I need to do is figure out when this is equal to 0. Well, that's pretty easy when x is equal to 1. And then I also need to find the asymptotes. And the asymptotes for a rational function is going to be when the bottom is equal to 0, provided that the fraction is simplified, it's reduced as much as it can be. Well, the top, x minus 1 and x plus 1, I have factored the top and bottom as much as I can. There are no common factors. This is a simplified fraction. So all I need to do is figure out when the denominator is equal to 0. Oh, and that happens, I can move the 1 to the other side to see that that's when x is equal to negative 1. So our function is going to have an asymptote at x is equal to negative 1, and is going to cross the x-axis at x is equal to 1. So when I can do this right here. So if I draw my number line, we'll have 0, we'll have negative 1, and we'll have 1. Our function may switch from positive to negative on both sides of negative 1. And it could switch from being positive to negative or negative to positive as we cross over 1. We simply don't know where the function is going to be positive or negative. However, we do know that to the left of negative 1, if we can find one point that's positive, it's all positive. If we can find one point that's negative, it's all negative. So we only need to test one value to the left of negative 1, one value between negative 1 and 1, and one value to the right of 1. So let's do that. Our three intervals, one is to the left of negative 1, one is in between negative 1, let's give myself a bit more space. One is in between negative 1 and one is to the right of positive 1. So a test value for over here, maybe I could plug in negative 2. That's a number inside of this interval. Between negative 1 and 1, well, 0 is between there, and 0 is an easy number to work with. I'll use that one. And 2 is bigger than 1, so I'll plug 2 into this function. So again, here is the inequality. So I want to plug negative 2 in over here and see, is it greater than 0 or is it less than 0? I'll plug in 0 and 2 as well. So let's plug in negative 2. So I've got negative 2 minus 1 over negative 2 plus 1. If I simplify this, negative 2 minus 1 is negative 3. Negative 2 plus 1 is negative 1. And negative signs cancel. So this is going to be positive. So in the region to the left of negative 1, this is going to be positive. Let's look at 0. So I'll have 0 minus 1 over 0 plus 1. Yep. So I'll have negative 1 divided by 1, and this is going to be equal to negative 1, which is less than 0. So in between negative 1 and 1, I will have negative numbers. And then how about to the right over here? If we have 2 minus 1 over 2 plus 1, this is 1 over 3, which is certainly a positive number. So we were looking for, when is this fraction going to be greater than or equal to 0? So we know it's in this region and in this region, and we'll have to worry about the boundary points as well. So our answer, so we know that the region from negative infinity up to negative 1, I'm going to leave that for a second, and the region from 1 to infinity is going to be all positive, but we have to include where our fraction is equal to 0. So here we have to be a little bit careful. Our fraction is equal to 0 when x is equal to 1, so I need to include 1 in my interval. My function has an asymptote at negative 1. Why? Because if I plug negative 1 into my function, I'm dividing by 0, and I can't do that. So I can't plug negative 1 into my function. I can't include negative 1 in this region. It's not part of the domain. So here's my answer. We have the region from negative infinity to negative 1, and the region from 1 up to infinity. This is all quite nice. So I want to finish with an application. So this formula here is fairly simple to remember, and this is the height of an object that is what would be called in free fall, meaning that nothing is affecting it other than gravity. So our function here, s, is the height of the function. So s of t is going to be the height of this object at time t. And the height is going to be measured in feet, and t is going to be measured in seconds. But this does depend a little bit. So there's v naught here, and there's s naught. So v sub 0 and s sub 0. And these are the initial velocity and the initial height. So when we think about, so for example, if we were going to throw a baseball up into the air, we apply a little bit of force to begin with, but once the ball leaves our hand, the only thing affecting it is gravity. So the v naught is going to be the initial speed of the object. And it could be that, if we're throwing a baseball up into the air, it will have a positive velocity. It's going up, and the initial height of the baseball will be however high I'm reaching up when I let go. It's not going to be at 0, which would be right at the ground. If we were throwing this up off the top of a building, we would be up higher yet. So this is just the initial height of the object, and v naught is the initial velocity. So let's do a quick example. An object is propelled straight up from the ground. So we're starting at ground level at 80 feet per second. For which interval of time is the object more than 64 feet above ground? So we have our formula here. So let's write down what it is we're trying to find. So we want the position to be greater than 64 feet. We want the height of the object to be greater than 64 feet. Okay, so this is what we're trying to solve. However, we know what s of t is. This is going to be negative 16 t squared plus v naught times t plus s naught is going to be greater than 64. And again, we have a little bit more information as well. V naught is the initial speed, and we're going 80 feet straight up. So v naught here is going to be 80. If the speed was going down, we would want a negative speed. And the initial height of the function, we're going right up from ground level. So we're starting right at the ground. So the height in feet is going to be 0. So we want to know, when is this greater than 64? And to be completely honest, this is exactly the kind of thing that we've been looking at before. So to start with, we write our polynomial on one side so that this is just going to be greater than 0. This guy here, if we excuse me, we're trying to solve when is this equal to 0, and I went ahead. Oops, this should be 80. I went ahead and did this off screen. So this is in fact going to be equal to negative 16 times x minus 1 times x minus 4. So when is this equal to 0? When x minus 1 is equal to 0, and when x minus 4 is equal to 0. So when x is equal to 1, or when x is equal to 4. And with a little bit of intuition, we can see when is the height of our object going to be greater than 64. Well, we're going to be moving up first. We're going to pause. The objects will move up, pause, and then come back down. So in this region here, in between 1 and 4, that's when our object is going to be the highest. So this is going to be our answer.